Hello students, welcome to the lecture on petroleum refining, and after this lecture, we will be able to learn the following objectives. Explain the flow diagram of a typical petroleum refinery, describe the refined products and qualities, discuss on alkylation and isomerization, define importance of energy for crude oil processing in oil refineries, understand techno-economic aspect of process efficiency and effectiveness in an oil refinery. Let's start with the concept of petroleum refining. Petroleum refining processes are the chemical engineering processes and other facilities used in petroleum refineries, also referred to as oil refineries, to transform crude oil into useful products such as liquefied petroleum gas, LPG, gasoline or petrol, kerosene, jet fuel, diesel oil and fuel oils. Petroleum refineries are very large industrial complexes that involve many different processing units and auxiliary facilities such as utility units and storage tanks. Each refinery has its own unique arrangement and combination of refining processes largely determined by the refinery location, desired products and economic consideration. There are most probably no two refineries that are identical in every respect. Some modern petroleum refineries process as much as 8 lakhs to 9 lakhs barrels, 1,27,000 to 1,43,000 cubic meters per day of crude oil.
Refining of petroleum. Petroleum is obtained by drilling holes or oil wells into the earth's crust. When a well is drilled through the petroleum-bearing rocks, usually natural gas comes out first with a great pressure. This is followed by crude oil, which comes out due to the gas pressure. Petroleum is separated into its constituents by the process of fractional distillation. Fractional distillation of petroleum is done by using a tall fractionating column or fractionating tower as shown here. Crude petroleum is heated to a temperature of about 400 degrees Celsius in a furnace, and the vapors thus formed are passed into a tall fractionating column from an inlet at its base. As the mixture of hot vapors rise in the column, it starts getting cooled gradually. Due to this, the vapors of the higher boiling fractions of petroleum condense first in the lower part of the tower, but the vapors of the low boiling fractions rise up into the tower and condense later. In this way, the fraction of petroleum having the highest boiling range is collected in the lowest part of the fractionating tower. The fraction having the lowest boiling range is collected in the topmost part of the tower. The various fractions that are obtained by distillation of crude petroleum are tabulated here.
Let us now discuss the flow diagram of a typical petroleum refinery. Petroleum is a complex mixture of organic liquids called crude oil and natural gas, which occurs naturally in the ground and was formed millions of years ago. Crude oil varies from oil field to oil field in color and composition, from a pale yellow, low viscosity liquid to heavy black treacle consistencies. Crude oil and natural gas are extracted from the ground, on land or under the oceans by sinking an oil well, and are then transported by pipeline and or shipped to refineries where their components are processed into refined products. Crude oil and natural gas are of little use in their raw state. Their value lies in what is created from them: fuels, lubricating oils, waxes, asphalt, petrochemicals, and pipeline quality natural gas. An oil refinery is an organized and coordinated arrangement of manufacturing processes designed to produce physical and chemical changes in crude oil to convert it into everyday products like petrol, diesel, lubricating oil, fuel oil, and bitumen. As crude oil comes from the well, it contains a mixture of hydrocarbon compounds and relatively small quantities of other materials such as oxygen, nitrogen, sculpture, salt, and water. In the refinery, most of these non-hydrocarbon substances are removed and the oil is broken down into its various components and blended into useful products. These components are separated from the methane at a gas fractionation plant. Petroleum hydrocarbon structures. Petroleum consists of three main hydrocarbon groups. Paraffin. These consist of straight or branch carbon rings saturated with hydrogen atoms, simplest of which is methane CH4, the main ingredient of natural gas. Others in this group include ethane C2H6 and propane C3H8. Hydrocarbons. With very few carbon atoms C1 to C4 are light in density and are gases under normal atmospheric pressure. Chemically, paraffin is very stable compounds. Naphthenic. Naphthenic consists of carbon rings, sometimes with side chains saturated with hydrogen atoms. Naphthenics are chemically stable. They occur naturally in crude oil and have properties similar to paraffin. Aromatics. Aromatic hydrocarbons are compounds that contain a ring of 6 carbon atoms with alternating double and single bonds and 6 attached hydrogen atoms. This type of structure is known as a benzene ring. They occur naturally in crude oil and can also be created by the refining process. The more carbon atoms a hydrocarbon molecule has, the heavier it is, the higher its molecule weight, and the higher it is the boiling point. Small quantities of a crude oil may be composed of compounds containing oxygen, nitrogen, sculpture, and metals. Sculpture content ranges from traces to more than 5%. If a crude oil contains appreciable quantities of sculpture, it is called sour crude. If it contains little or no sculpture, it is called sweet crude. Every refinery begins with the separation of crude oil into different fractions by distillation. The fractions are further treated to convert them into mixtures of more useful, saleable products by various methods such as cracking, reforming, alkylation, polymerization, and isomerization. Petroleum products. All products comprise refinery gas, ethane, LPG, aviation, gasoline, motor gasoline, jet fuels, kerosene, gas or diesel oil, fuel oil, naphtha, white spirit, lubricants, bitumen, paraffin, waxes, petroleum coke, and other oil products. Oil products are any oil-based products which can be obtained by distillation and are normally used outside the refining industry. The exception to this are those finished products which are classified as refinery feedstocks. Aviation gasoline. Aviation gasoline is motor spirit prepared especially for aviation piston engines with an octane number suited to the engine, a freezing point of -60 degrees Celsius, and a distillation range usually within the limits of 30 degrees Celsius and 180 degrees Celsius. Bitumen. Bitumen is a solid, semi-solid or viscous hydrocarbon with a colloidal structure which is brown to black in color. It is obtained by vacuum distillation of oil residues from atmospheric distillation of crude oil. Bitumen is often referred to as asphalt and is primarily used for surfacing of roads and for roofing material. This category includes fluidized and cut back bitumen. Ethane. Ethane is a naturally gaseous straight chain hydrocarbon C2H6. It is a colorless paraffinic gas which is extracted from natural gas and refinery gas streams. Fuel oil. Fuel oil defines oils that make up this distillation residue. It comprises all residual fuel oils, including those obtained by blending. Its kinematic viscosity is above 10 CSD at 80 degrees Celsius. The flash point is always above 50 degrees Celsius and the density is always higher than 0.90 kg per liter. LPG. Liquefied petroleum gases are light hydrocarbon fraction of the paraffin series derived from refinery processes, crude oil stabilization plants, and natural gas processing plants comprising propane C3H8 and butane C4H10 or a combination of the two. They could also include a propylene, butylenes, isobutene, and isobutylene. The LPG is normally liquefied under pressure for transportation and storage.
Have you ever stopped to think about the many uses oil has in our day-to-day lives? Oil gives us hot water, heated homes, and electricity, to name only a few of its best-known uses. But oil is much more. Did you know that everything from your jumper to a DVD to a scented candle comes from oil? even a water bottle, or the detergent you use to wash your clothes. Whether by land, sea or air, the uses of oil are endless. The gasoline and diesel that power farm equipment are products of refined oil, and the crops that equipment is harvesting, all protected by oil-based fertilizers and herbicides. It is the fuel that lets us take to the skies and sail the 7 seas. Oil even helps to keep us safe and healthy. Without oil, hospitals wouldn't have such refined products as everyday pills and nylon bandages, or such essential devices as saline solution bags and surgical tubing. Everywhere you turn, oil is playing a part. It is an essential part of our lives. Even just a simple stroll down the street is improved by oil. The asphalt under your feet, the traffic lines painted in the street, even the coating on terraces and patios. All brought to you by oil. And of course, where would we be without the gasoline and lubricants used to drive our vehicles? Oil really is a fascinating product.
Now moving on to the next topic, we will study the refined products and qualities. Crude oil is processed or refined to produce usable products such as gasoline. The process is very complex and involves both chemical reactions and physical separation. Crude oil is composed of thousands of different molecules. It would be nearly impossible to isolate every molecule and make finished products from each molecule. Chemists and engineers deal with this problem by isolating mixture of molecules according to the mixture boiling point range. For example, gasoline molecules might boil in the range from 90 to 400 Fahrenheit. Home heating oil could be from molecule mixes that boil from 500 to 650 Fahrenheit. For convenience, the mixture of fractions are given a name. Product specification. Gasoline fill up. Most people is familiar with gasoline octane number. It is the number that refers to when selecting the grade of gasoline to use in car. The number may be 87 or 89. The vehicle manufacturer recommends a certain type of fuel to be used. In most cars, this is 87 octane unleaded gasoline. This octane rating is actually the average of 2 tests that are run on the finished gasoline, the research octane and the motor octane. The average is the road octane or R plus M by 2, which is posted on the pump. Some of us may remember when gasoline was sold with a research number. Gasoline is blended to meet the following specification. Read a vapor pressure RVP, which is a measure of hydrocarbon vapors and is needed for starting engine. Octane, which is a measure of anti-knock level of gasoline and is important because knocking lowers engine efficiency and wastes power. Toxins, which are measures of the harmful components in gasoline and refines, are required to benzene, olefins and sulfur levels. Oxygen content in reformulated gasoline to reduce the level of greenhouse gas emission. Refinery operation. Refinery operations are composed of many different operating units that are used to separate fractions, improve the quality of the fractions, and increase the production of higher value products like gasoline, jet fuel, diesel oil, and home heating oil. Crude oil distillation. Crude oil distillation is used to separate the hydrocarbons in crude oil into fractions based on their boiling points. The separation is done in a large tower that is operated at atmospheric pressure. The tower contains a number of trays where hydrocarbon gases and liquid interact. The liquids flow down the tower and the gases up. Vacuum distillation. The residual fraction 650 of and higher boiling material from the crude tar can be sent to fuel blending to produce residual fuel oil or number 6 fuel oil. Often this residual fraction is further separated into vacuum gas oil and vacuum residue. This unit is operated at a slight vacuum. This allows the hydrocarbons to be separated at lower temperature and prevent undesirable chemical reaction that would burn the material and produce petroleum coal. The vacuum gas oil is sent to the catalytic cracking unit for further processing. Catalytic reforming. Catalytic reforming is used to improve the quality of naphtha from the crude distillation unit. The catalytic reforming unit uses a catalyst to allow the chemical reaction to take place under reasonable temperature and pressure and encourage the desired hydrocarbons to be produced. Catalytic cracking. Catalytic cracking is a very important process in the modern refinery. The process allows the refiner to convert material that would normally be burnt as fuel vacuum gas oil into gasoline and distillate home heating oil and diesel fuel. One only need examine the price difference between residual fueled oil and gasoline to see why this is an attractive alternative. This process breaks or cracks long-chain hydrocarbons into smaller molecules in the naphtha and distillate boiling range to increase gasoline and diesel production. This process will yield 50 to 60% gasoline, 20 to 30% distillate, and 30% butanes and lighter. If one does the math, we'll see that the volume of products is greater than the volume of the feed. This is because the long-chain hydrocarbons are broken into smaller ones. Let's know the meaning of alkylation and isomerization. In the alkylation process, isobutane is reacted with either isobutylene or propylene to form complex paraffin isomers. The reactions takes place in the presence of hydrofluoric or sulfuric acid catalyst. By combining these molecules, the octane level of the paraffin isomer or alkylate is increased to around 93 to 96 octane. Refiners use this process to improve the octane level of the gasoline pool. Light naphtha 90 to 190 Fahrenheit can have its octane number improved by the use of an isomerization process to convert normal paraffin into their isomers. This results in an increase in octane number as evidenced by increase in normal pentane 62 octanes to isopentane 92 octanes. The process uses a platinum catalyst like alkylation. This process improves the octane quality of the gasoline pool. Hydrotreating. Hydrotreating is a process where a petroleum fraction is reacted with a hydrogen for the purpose of removing impurities. The process is usually used to remove sulfur. Hydrotreating processes use hydrogen from the catalytic reformer or a hydrogen plant. Product blending. Product blending is where the different petroleum fractions are combined together to make the final product. Refinery complexity. Refinery at night, not all refineries are the same. Refineries can range in size from small units capable of processing 10,000 BD of crude oil to giant complexes running on 7 lakhs BD of crude oil. The United States has 150 refineries with a combined capacity of 17.6 barrels per day of refinery capacity. In 2008, the average refinery utilization was 85.4%. Nearly 48% is located in U.S. PADD 3, which includes Texas, Louisiana, Arkansas, and New Mexico. Refinery economics. Refinery economics are largely a function of supply and demand. Product prices are determined by a variety of factors such as economy, weather, and competition between retailers and from other fuels. Feedstock prices, crude oil, are influenced by the above demand factors, actions by OPEC and governmental regulations. The oil refining process starts with a fractional distillation column. The problem with crude oil is that it contains hundreds of different types of hydrocarbons all mixed together. It has to separate the different types of hydrocarbons to have anything useful. Fortunately, there is an easy way to separate things, and this is what oil refining is all about. Different hydrocarbon chain lengths all have progressively higher boiling point, so they can all be separated by distillation. This is what happens in an oil refinery. In one part of the process, crude oil is heated and the different chains are pulled out by their vaporization temperature. Each different chain length has a different property that makes it useful on a different way. How are crude oil and refined products transported? Crude oil tanker loading facility. Crude oil must be moved from the production site to refineries and from refineries to consumer. These movements are made using a number of different modes of transportation.
Between 2002 and 2011, 10 P-MAX ships were built for Concordia Maritime at the Brodo-Split shipyard.
Safe navigation in narrow waters and maximized cargo intake is the idea with the P-MAX project. We have managed to achieve that and quite a bit more.
The new Stena P-Max, with a deadweight of 65,000 tons capacity, is probably the safest MR tanker ever. It's an Ice Class 1B product tanker with a length of 183 meters, which is the same as a traditional MR tanker, but with a width of 40 meters. The P-Max has a wider hull than a standard MR tanker. At the design draft, 11.3 meters, it can load 30% more cargo than a standard MR tanker. At full draft, 13 meters, the P-Max can take as much as 45% more cargo than conventional competitors of the same size. The ship has a full double hull, and in addition to this, the vessel has dual operation and control systems. There are 2 engine rooms completely separated by fire and watertight bulkhead. All control systems are redundant, and each engine has its own fuel system. This means that the machinery systems work independently of each other, which is obviously a very big advantage in terms of safety. As the result of the dual propellers, dual rudders, and twin steering gears, the P-Max can make faster and tighter turns than a traditional MR tanker. That is a big advantage in both efficiency and safety. Proactive safety will soon become the entry ticket to sensitive waters around the world. These areas are growing not only in number, but are often closed to the oil-dependent markets. Therefore, proactive safety is a key to long-term business. Safety is ultimately an environmental issue. The flexible fuel oil system offers the possibility of using low-sulfur fuels in sensitive areas. Clever hull design also helps to limit fuel consumption, and the speed characteristics are as good or better compared with standard tonnage. The bridge is designed with a 360-degree view, and the integrated bridge control system is located centrally on the bridge, with immediate access to all information required for monitoring, as well as all controls. In addition, the bridge is fitted with a co-pilot system, which facilitates education and training, a major benefit for safety in narrow waters. The P-Max is designed to carry clean or dirty products as well as crude oil. It has a certified effective cleaning system and smooth cargo tanks. That means that you can quickly change from one product to another with minimal risk of contamination. Cargo operation is further enhanced by corrugated bulkheads in the tanks, which reduces the remaining amount of cargo on board after discharge. There is much to gain by saving time and protecting the cargo from contamination. It is cost-effective. The concept is straightforward. Achieve real safety, more flexible trading, and low transport costs through innovative thinking and the best technology.
Importance of energy for crude oil processing in oil refineries. A large amount of energy is used in oil refineries for crude oil processing. A refinery itself can ensure all the utilities required for its operation by means of more or less complex energy transformation using a part of the products obtained by crude oil processing. Therefore, crude oil for a refinery presents not only a feedstock but also the main source of energy required for crude oil processing. This fact aggravates a clear separation of a refinery utilities system from crude oil processing. Today, in oil refineries, the share of crude oil used for energy generation is in the range of 4 to 8%, depending on the refinery complexity level. Complexity, that is a depth of crude oil processing, is increased as the range of products and the number of so-called secondary units is enlarged. The level of energy requirements in an oil refinery is increased by the level of complexity, and it is expressed as follows. As a share of energy consumption in total quantity of crude oil processed, or as a specific energy consumption per ton of processed crude oil as per ton of generated refinery products. The dependence of specific energy consumption on complexity leveled and oil refinery efficiency is shown in the figure. It can be clearly seen that the level of energy requirements is increased by the level of complexity, and that the oil refineries with the same level of complexity can have low and high level of energy efficiency. The difference between energy-efficient oil refineries line B and energy-efficient oil refineries line A is a real possibility for rationalization of the energy consumption in energy-inefficient refineries. Inefficient refineries can decrease their internal energy consumption by 20 to 30% by using more efficient technological, energy and organizational solutions. Techno-economic aspect of process efficiency and effectiveness in an oil refinery. Refinery efficiency and effectiveness are analyzed through the cost prices of semi-products and finished products. The emphasis is placed on the problems and dilemmas that the management of refinery units and the refinery as a whole have to face when choosing the cost pricing methods for the semi-products, which are then blended into finished products in the final phase and then sent to the market. Complexity of crude oil processing. Complexity of the possible refinery product cost pricing methodology, that is, it can be seen that the crude oils are mixed when passing through the refinery units. This demands attentive monitoring of each unit input or output as well as distributing the cost to the bearers of cost using computers and multidisciplinary expert teams from inside and outside of the petroleum companies. The complexity of possible methodology for determining the refinery product cost prices is dependent on the complexity of crude oil processing. Finished product cost prices are calculated by multiplying the quantity and cost prices of semi-products. The semi-products blended into particular finished products often originate from several refinery units, as for example, in the case of gasoline, which is the result of blending the semi-products from 8 refinery units: crude unit, vacuum residue, tire breaking unit, fluidized catalytic cracking, alkylation, gas concentration unit, gasoline reinstallation, aromatics extractions, and catalytic reforming. The procedure for determining the cost prices of finished products has 3 phases. In the first phase, the total refinery costs are distributed to the refinery units. In the second phase, the costs of each mentioned unit are distributed to semi-products which are obtained on these units. It must be pointed out that the effect of choice of calculating basic on the level of refinery products cost prices is of extreme importance, and therefore the choice of one of the following methods must be made very carefully. Density method, thermal value method, average production cost method. These methods are convenient for determining the semi-product cost prices by using elective division calculation with equivalent numbers. However, advantages and disadvantages of each method should be taken into consideration. Besides the importance of the choice of calculating base for determining the equivalent number, the choice of reference derivative is also important, but less so than the choice of calculating base. Determining the byproducts of every refinery unit as well as their treatment in the procedure of applying the elective division calculation with equivalent numbers also appears as a problem which the management of a refinery has to contend with. In the third phase, semi-products are blended into finished products, although it often involves the blending of 10, 15 or even more than 20 semi-products at calculated semi-product cost prices. With the inclusion of initial and final stock of semi and finished products, the phase itself does not present a problem. The sales value allocation method and the byproduct method are methods frequently encountered in determining the cost prices of products. The sales value allocation method is one of the simplest cost determination methods frequently encountered. According to this method, the cost price is determined in such a way that the sales value of oil derivatives is decreased by actual profit in an equal amount for each of derivatives and or increased by actual loss also in an equal amount for each of derivatives. The positive aspect of this method is its simplicity and the possibility of cost price determination in a very short period of time. Now, in the end, let us summarize what we have learned in this lecture. Petroleum refineries are very large industrial complexes that involve many different processing units and auxiliary facilities such as utility units and storage tanks. Petroleum is a complex mixture of organic liquids called crude oil and natural gas, which occurs naturally in the ground and was formed millions of years ago. An oil refinery is an organized and coordinated arrangement of manufacturing processes designed to produce physical and chemical changes in crude oil to convert it into everyday products like petrol, diesel, lubricating oil, fuel oil, and bitumen. Refinery processes have developed in response to changing market demands for certain products. With the advent of the internal combustion engine, the main task of refineries became the production of petrol. A refinery itself can ensure all the utilities required for its operation by means of more or less complex energy transformation using a part of the products obtained by crude oil processing.